Hi everyone. Today I'm going to talk about some of the work that we've been doing for materials modeling algorithms at Phasecraft. And so maybe just a couple of words on who we are. So Phasecraft is a quantum algorithms startup based in out of London and Bristol. We raised the Series A round last year, and our focus is on developing algorithms for near-term quantum applications. So what we have here on the kind of left-hand side is some of the recent works we've been doing over the past maybe 5 years or so, all the way from kind of basic with a focus on efficiency and assuming that these near-term devices will be very noise-prone, so we're going to have to run kind of optimal near-term quantum algorithms. So what we have is kind of applications that are typically for kind of prototypical systems that are representative of materials, things like efficient encodings, different ways to model dynamics, how to obtain ground state properties, also for our take on optimization algorithms. Today I'll focus on our kind of more research on the kind of quantum material space, and to just give a bit of some context for this is that, okay, I don't need to explain here, but we know that kind of classical computers are very important and very powerful, but there are some very important problems that classical computers just can't provide efficient solutions for. And having quantum computers can radically change this landscape. In some of this context, we might consider kind of computer-driven materials discovery one of those applications. And just to give kind of maybe some state of the art, if we take the Fermi-Hubbard model, which is a prototypical model for strong electron interactions in materials, it still remains unsolved despite, intensive research for at least 50 years. Like back now, 20 years ago, there was the kind of biggest attempt at solving this exactly, and it was pushing the absolute limits of supercomputers at the time, and it still does so. So we're talking in this system, you have like 17 electrons, and then kind of orbital sizes is somewhere between 20 and 30, and this is just far too small to model effectively any kind of get some advantage in real materials. So we really are limited at our kind of classical compute solve for these types of problems. And also what seems like a long time ago now, but in 2019 Google had their milestone experiment where on their Sycamore chip of 53 qubits they ran an algorithm for about 20 time steps. But if you believe some sort of resource estimates, if you wanted to model nitrogen fixation or just other applications, we would need the scale of about 10 to the 9 qubits with 10 to the 15 time steps. And so even though we have a good idea of what problems we want to solve or where they could find some benefit with quantum computers, there's a huge gap between the small noisy hardware that we have today and algorithms that need to be dramatically improved to run kind of get applications. So in the kind of context of simulation time and length scales, here we are kind of, so materials modeling spans very large length scales and time scales. Quantum simulation of materials will act on the shortest time scale, so this is at femtoseconds, and the kind of also very short length scales. So this is about angstroms. So we're kind of in the box here towards the left, and this is when we want to model electronic properties. Typically, if we want to model this classically, if we want high accuracy, we have to pay a huge cost, and typically to get exact answers, this will be exponential cost or something that will be kind of high polynomial cost. The typical methods would be something like density functional theory, this would be for materials, and then things like full configuration interaction for molecules, and quantum Monte Carlo is another alternative techniques. But all of these are limited by the kind of classical approximations that you must make to solve big systems. With quantum computers, they fundamentally can overcome these limitations effectively by how we set up the problem and what type of properties we want to obtain because of the kind of covering the exponential Hilbert space. Now, just as an illustrative example, if you wanted to design something like a new battery, this is just kind of a cartoon of, like a lithium-ion based battery where you have anode, cathode, and then the lithium crosses the electrolytes. So, but when you're designing new batteries, you will have to, have many constraints you need to satisfy. In this case, you want to have good high energy density. It needs to be safe. Needs to operate at room temperature, etc. And effectively, having a good predictive tool is at the kind of bleeding edge of material science to use this. And if we aren't modeling things like strong correlations properly, there's whole regions of the periodic table that we can't access due to our classical tools. So having access to a new tool based on quantum simulations is quite promising. The proposition is promising. And so here I'll kind of discuss how we at Phasecraft with our work are bringing materials modeling with in touching distance for some quantum practical advantage. So this is our approach, which is detailed in the paper, the Nature Communications paper below, like at the bottom. So let's say we want to describe some material. In this case, I'm just demonstrating a transition metal oxide, which, this is just, if you tile this in space, it becomes periodic, and then it has some functionality that you can exploit in an experiment or in a technology. What we do to set up this problem is we use density functional theory. This will kind of, you input the cell of the material, so basically where the atoms are, and then you solve that classically, and you represent the orbitals. So this kind of funny cartoon below, this is where the electrons can be in the system. And this is represented in a maximally localized basis set called the Vanier basis. We need this because our quantum algorithms exploit this locality. Then you have to have an encoding, so this is how you represent your electronic modes on the for the quantum computer. We do this in an efficient way known as our hybrid compact encoding. Then you have to have an algorithm. This algorithm will extract properties about the system. So here we could set up an algorithm that does dynamics, so you let the system evolve, or you want to compute something like a ground state property, like an energy or a density distribution. And this is, your algorithm will be tailored to what you want to ask about the system. We've encapsulated this in a tool chain at Phasecraft, so we can kind of put materials through this entire tool chain, and we use our multiple layers of optimizations, with the final one being an optimized measurement protocol. So this is how do we actually extract information about the material that we care about. So if you want to have, for example, an energy or a density that scientists then can use to inform about the functionality of that system. Okay, so in a bit more kind of technical detail, here this is the Hamiltonian that we use to simulate the material. So this is just the electronic Hamiltonian within something known as the Born-Oppenheimer approximation. So here the ions remain fixed, but the electrons are allowed to be dynamic. Importantly, we get the coefficients of the Hamiltonian. So these are this Coulomb tensor and the hopping matrix elements come from the DFT calculation, where the phi inside the integrals is the Kohn-Sham wave functions. However, these are the block wave functions here, but we use them within the maximally localized basis set. So here, effectively, you're doing a well-known approach in the literature, which can give you real space representations that have minimal spatial spread. This will be important later on when I show some of our results for what are the resource estimates for some materials. Importantly, what I have also up here is something known as electronic band structure, which many material scientists will use to diagnose what is this material doing. So here I'm just highlighting an area that kind of covers these kind of three bands, so to speak, and we call this an active space approximation. So what we're saying is that we're going to represent our Hamiltonian only within this region, and we will only assess the functionality within this region. This is a common approach that people use in both chemistry and material science to make your simulation that you're trying to do a bit more tractable on classical computers, and also, in this case, for a quantum algorithm. So the two quantum algorithms that we cost here are the variational quantum eigensolver and classical or time dynamic simulation. So what do these look like as a kind of picture? Here we'll have effectively a kind of circuit. So as I was saying earlier, you have these localized orbitals. They are encoded onto a qubit register. So this is where the information is stored about that electronic mode. So you can think of, if I'm a material scientist and I care about something like my, I don't know, my transition metal D states, these can be encoded inside the qubit registers. Then you have to have an initial state preparation. These are these red gates called Gibbons rotations. And then you implement your algorithm. So this could be the variation quantum eigensolver, or it could be time dynamics. And at the very, very end, you get something here at the side, the very right-hand side, which is this parameterized quantum state, which you can do measurement on. So these theta parameters are variationally optimized in a classical outer loop, and on the inner loop, you are just evaluating energies on this state. You do this iteratively until there is a convergence. And at convergence, you can estimate ground state properties of the system of VQE. So here, again, this is this active space approach, where in the highlighted region, there are 3 bands. So these are just effectively telling us like the kind of energy states that these electrons can occupy. They are represented in real space, kind of in the middle with the kind of the lobes, the spherical lobes. So this is saying my electrons occupy this type of spatial state. And this is for this material strontium vanadate, which is known to be classically challenging to model. It has strong electron interactions, and it is it is a correlated metal, but can be tuned to be a Mott insulator with various experimental probes. So we resource estimated effectively what's important here is to look at like how much quantum resource do we need to model the system. So we have 3 bands which translate into 180 qubits when we tile our lattice, and we see that we get a depth that is in the region of hundreds. Compared to the previous baseline, this is separated by 6 orders of magnitude for strontium vanadate. So we saw earlier the nitrogen fixation problem, which required something like 10 to the 15 gates. Here we're going from something like 10 to the 8 all the way to 10 to the 2. So with actually clever techniques in the whole stack, you can reduce these quantum resource estimates by quite a margin, such that we're getting within touching distance of kind of practical quantum advantage for maybe ground state properties. Another application I'm just highlighting is lithium copper oxide, which is known to be high capacity battery cathode. This is just kind of a highlight slide of our kind of improvement over the previous state of the art. So the approach is, in our tool chain, we can feed in the unit cell of a material, output a circuit, and do resource estimation on it. And in all cases, we see quite significant improvements. We also have these improvements stored online. You can access it here at materials.phasecraft.io with all of the kind of metadata and various different details about how the information is passed through our tool chain. So that's free to use, so please go there and have a look. There's a wide collection of different materials there with different properties, different functional properties. Things go all the way from like hydrogen applications, fuel cells, batteries. If you can kind of think about it, it's probably there. And we kind of have varying degrees of kind of qubit numbers and depths for these materials. Okay, so in the second part, I'd like to talk about a recent work we did, which is, so in the previous work is how are we developing resource estimates for these VQE or time dynamics algorithms, so how big does my machine need to be? Here, instead of using density functional theory as the seed to set up that problem, we actually want to enhance density functional theory. So how do we go about doing that? So the details are detailed in the paper on screen. One thing that like the formalism of DFT takes into account is classically it's based on the approximation you use for something called the exchange correlation energy. And due to this successful classical parameterizations, the whole success of DFT effectively relies on that, of course, but also efficient classical implementations of the algorithm. So what the idea here is that we use data from a near-term quantum device, we're assuming that, to parameterize the XC functional. Some things that you might think that are important when you're representing your system that you want to get the XC energy of is how do we represent it? So what's the optimal way to do that in its Hamiltonian formulation? What encodings we use and what measurement protocols are also involved in the algorithm that is run. So these are, ways you can optimize the algorithm to give you higher quality results, but the algorithm is independent of the submodule you use for any of these encodings or measurement protocols. But so you input the system, it's run on your quantum device, and it outputs a value for the exchange correlation energy for, in this case, a given density value. We have two modes this runs in. The algorithm can run in an online mode, which is when you want to implement a classical DFT loop. So now we have some information on this exchange correlation energy. Then we execute a classical DFT loop, which will be run on a classical computer. So DFT scales polynomial to the power of 3. This can be run on, for very large system sizes. In the online approach, the exchange correlation potential and energy are queried at each DFT iteration. In the offline approach, you store the exchange correlation energy in some parametric functional form, and then you query that. So that you're actually you run your quantum computation once, and then you parameterize this functional, and you use it in your classical loop inside this formalism of cone-sham density functional theory, which is the typical kind of implementation of DFT for materials and molecular modeling. And once you converge your classical algorithm, you will have, if your functional approximation is sufficient, you will have information about the ground state of your system. So in terms of where we kind of showcase this, we showcased it for the Hubbard model. So this is in the formulation of lattice DFT. So this is, as I said earlier, this is a very challenging classical condensed matter problem that has no solution beyond dimensions equal 1. But so here we set up a Hubbard model in a confining potential. So imagine you have a chain of ions, you can have fermions occupy those systems, and you put it into a quadratic potential. So this is a model, I will preface that. But a material, I mean, in 3 dimensions, basically material is generated by an external potential due to the ions in the system. So we solve this with DFT. So what does that mean? That means at the end of the DFT algorithm for this system, we produce a density distribution as well as energetics. But what I want to highlight here is that for this 1D Hubbard system, our QE DFT functional based on VQE simulations in the offline form, so we're running classical DFT with a quantum functional, produces these shoulders above. These shoulders are due to, they're called incompressible Mott regions of the phase diagram. So basically your fermions get stuck, so they can't move, they're stuck to fixed occupation at 1. And conventional DFT approaches, in this case Hartree-Fock, fails to pick up those features because those features are due to strong interacting electrons. So here's a qualitative feature that the classical conventional DFT is missing, but with the quantum enhanced functional, we can apply it. And you might notice this is for a 1/200 system. We actually used data from a 1/8 system from the Google Sycamore chip. We parameterized our functional offline, so that gives you a continuous representation of the functional, and then you can use it for a much larger system. So this is the third point that I make here, that there is a number of advantages to this approach. It can be applied to much larger systems than the data you have generated it on. It actually doesn't rely on accurate quantum computations. We purposely left the VQE depth to be extremely shallow here, so we were using the Hamiltonian variational ansatz with depth 1 or 2, which is very modest, so that will be not enough to capture the ground state. But the properties of the functional itself, that you can impose constraints on it, and it is containing actual physical information, is some sort of robust error mitigation procedure, physically motivated one. And in all of our tests, when we were comprehensive in this, it usually always performs better than conventional Hartree-Fock DFT and always better than pure VQE alone. So this is asking, if I were to just run VQE on this confined potential model or 2D system, how does that work? And it will do better. So I just want to kind of leave here with a bit of a thought. So at Phasecraft, since it was founded in 2019, we've seen a millionfold improvement in kind of resource estimates for materials of technological relevance. We're now kind of entering the regime where we need to get another 100 improved fold to reach kind of current quantum hardware devices. And so a lesson from this, and maybe leave it to people in the audience, is basically, I think that like theory can beat Moore's law by multiple orders of magnitude. And this is important to take into consideration, that clever tricks on your algorithms in theory can really improve the kind of outlook for near-term quantum computation. So thank you very much.
Thanks very much, Evan. That was very interesting. So we have a couple of questions. So the first one is, how does QE-DFT compare to DMRG in one dimension?
So in one dimension, DMRG is the classical state of the art. So QE-DFT will, that line is effectively parameterized by DMRG computations. So it compares to it in one dimension.
Okay, perfect. Another question is, noisy quantum computers cannot access the full Hilbert space and are simulatable with, e.g., tensor network methods. So how low do you think, or did you study the effect of noise with the previous resource estimates? Is there any noise tolerance there?
So there's no assumptions made about the noise in those resource estimates. It's not assuming properties of the noise. In fact, we didn't run anything because we can't.
Yeah, right, yeah. Of course. I had one question. So everything you said about the resource estimates was assuming VQE is the algorithm.
In the results I showed, yeah, it's VQE, but we also have them for dynamics as well.
Right, okay. So for the VQE, did you take into account the measurement overhead for just the accuracy that you need for VQE?
Yeah, that's incorporated in not the results that we're quoting there, but it is incorporated in the paper.
Okay,
as
perfect.
well, yeah.
Yes.